Welcome to Composites Modeling using numerical methods. Today we'll be covering laminated composite structures versus sandwich structures. Again, I have invited Mr. Wade to help us guide us through the tutorial. What are the learning objectives of this particular tutorial? We would like to show that sandwich structures provide superior performance relative to bending compared to laminates. We'll also show in a later tutorial that composite sandwich structures also provide excellent buckling performance compared to laminates. So what are the benefits? If I were to compare a solid metal sheet or even a composite to sandwich construction or even a thicker sandwich construction, and these are referencing a hex web honeycomb attributes and properties, you will see that the relative stiffness of a thicker sandwich is going to be superior compared to that of the metal sheet. And that also is true if this was a composite sheet. You can also see that a sandwich structure will have superior strength compared to a laminate, which has no core. And then also the weight will be very minimally increased while also giving that extra benefit. So what are we doing here and why does it provide superior performance? What really happens is that by putting a face sheet on the top and a face sheet on the bottom, separated by a core that has relatively low properties, what you find is that the moment of inertia is increased quite a bit, very similar to an I-beam. And in an I-beam, you can see how you get superior bending performance, even though the center portion of the I-beam is relatively thin. So that is the same principle we're using here to achieve a superior stiffness and superior strength. There are many types of sandwich structures. There's cores made of foam, there are cores made of honeycomb, and there are other materials that can be used to achieve superior bending performance. You can also have a hexagon core. In this case, you're going to have the longitudinal direction of the hexagon core, and then you're going to have the transverse direction of the core. You can see here that there's two walls that are coming together, meaning that they're thicker in this particular section of the core. That's going to provide different properties in the L and the W direction. However, if I were to take the core and pull it along the L direction or pull it along the W direction, you will see that the properties are relatively small, and they're quite small because these are very thin foils that have been manufactured to then provide the particular bending performance we're looking for. Here, what I'm showing is the hex web honeycomb attributes and properties for honeycomb core. You can see in the first column what's provided is the cell size, the alloy, the foil gauge. And what you find is that as you go into higher packing density, you'll then achieve a higher packing density also means smaller cell size. You achieve higher properties, generally speaking. What you will see here in the second column is the packing density. Next, you're going to see the compression, bear strength, and stabilized strength of the particular system of interest. And this is in the E33 direction, the modulus transfer in the thickness direction of the core. And you can see here is provided the typical, but also the minimum value for the strength. The modulus is also provided. And next, you have the plate shear, which provides information relative to the transverse shear properties in the L direction and W direction. So, in other words, here I have the modulus data and the strength data that can be used to input that into the models. In these cases, you will have situations where there's corrosion resistant materials that will have superior performance than those that don't have under moisture conditions. These properties can now be used to our advantage, and we'll illustrate that with example problem of a material system here is ASF4 8552 unidirectional properties with the modulus provided along the various directions, the Poisson ratio, and shear moduli. The applied thickness to be considered is 0.009 inch. And then we also have the core properties. And you can see the core properties for this material system have a very relatively low, quite a bit low properties in the in-plane direction, which makes sense because we discussed how these in-plane directions do not really have a lot of stiffness. But through the thickness direction of the core, you can see that it has a finite amount of modulus here, and the Poisson ratio is quite large because the system behaves like an accordion. You can also see that the in-plane shear modulus is also relatively small, and you can see that G13 is greater than G23 because of the factors that we discussed. The core thickness in this example is 1/2 inch, and the properties provided here came from this particular paper at the bottom. Now, it is possible to estimate properties rather than finding them using a spec sheet. And if those were not exist, there might be ways to be able to estimate those properties. One approach that exists has been discussed here at the bottom paper. Here is a Python script that will do its best using the geometric information of the honeycomb core. It will try to then attempt to determine and estimate the properties of the system. I have a video tutorial that goes into significant amount of information, and it teaches you about the theory of sandwich structures, which is based on Reissner-Milling theory. And the theory allows you to simulate sandwich structures in a very effective way. And that is discussed in the description link. You will see that. The first example we'll consider today is a plate under bending. This plate will be a laminate, which is 0 plus minus 30, 0 symmetric. But then what we're going to do, we're going to take half of this laminate and put it on the top, and the mirror image will go at the bottom. We'll put a core, and what that's going to do effectively is you're going to have an increase in weight that's very small of 3 to 10%. Yet, we're going to see that the strains, when they're compared from the sandwich structure under this bending load applied, compared to the laminate, will provide superior bending performance than laminates with the same load. And now I'll pass it over to Mr. Wei, who will guide us through this particular tutorial. I appreciate your attention.
Compare the strain between these two structures to show that the bending performance of this sandwich structure behaves better than this only the laminate composite material under the same load. The material property is shown in the sixth slice. Here it shows the laminate material, and each composite layer is 0.09 inches. And the sandwich structure, there is a chrome, and the material property shows here the thickness is 0.5 inches. Okay, then we can go to the Abaqus. So in Abaqus, we can still use the shell model. We build a 3D shell model, the planner. So here I already set up the geometry. I make the length is 10 and the width is 1. For you guys, you can decide the dimension as you like. I make some partition because later I want to compare the string components around like this center. Okay. Then for the property, I create two material property. One is a laminate. So I input all the material components, use the engineering constant elastic property, and also improve the sandwich, the middle part material. So you can see the E1, E2 for that material is very soft compared to the laminate. And the E3, the third direction, that means in Z direction, that sort of compare these two have a very rigid, stiffer modulus. Okay. Then we can set up the composite material. We first build the material setup based on this laminate only. Okay, then we can set a region for this all the material, and the material property I set as laminate 1, and the thickness we set a uniform thickness 0.09 for each layer. Rotation is listed here. So the angle is based on the x direction, which is this actual direction, the length. Then, because this is a symmetric setting, so we just click this on. Okay. Then, for second case, for the sandwich-like sandwich structure, we still pick the whole region, but for the material, the first 4 layer, we use the laminate material, and then the last layer, we use the coal, and the total will 5 layers. As we click the section symmetric on, so that the first 4 layer, we still use 0.09 thickness, and the last layer, we know that the total core thickness is 0.5 inches. So the half of it will be 0.25. Then for the rotation angle, we just follow what here it is 0, 30 degree, negative 30, 0. And for the middle parts, we just set the angle as 0 here. Then click OK. Then we can assemble it. You click this, create an instance. And for the step, we just use normal static, general static setting. We don't need to change any other things. And for the output, because we are going to compare the string layer by layer. So for the domain, we would like to choose the composite layout. Then if you want to calculate the laminate structure, so you choose this laminate composite layout. If you want to calculate the sandwich structure, then you switch to the sandwich structure. And then we are asked for the string. Probably you can both for the stress, and then the section force. Then also we can request the displacement. You can just create another output field, and then ask the displacement U. Next step, interaction. Here I create a reference point. So you can use the true reference, then input the coordinate system. Then you can create a reference. And then I constrain this reference to this edge to make them move together in the direction. So I want a pure bending. So you can see my setup. I use the equation to constrain it. The first one is surface 1, is this surface, node on the surface. And the second one is this point. And then I constrain in the direction. The load, I fix the right side and then apply the load, the shear edge load. On the right side, I just make the force 10 pounds per inch. I set it negative to make it bend downward. And also, I fix this side. Okay, then for the mesh, for the total mesh, I use the quadratic structure mesh because the whole geometry is regular. And then the element type use shell and use full integration, linear full integration. Okay, then we can run the job. So I already run the job. 2 cases. One, the first case is doesn't have the structure. Second case is is sandwich-like material. We can see the results. Maybe first show the whole thing. Okay, because we want to compare like one by one. Then first we use option, click common. Then to make sure the deformation, the scale is 1. So you will not get, so it will reflect the real diffraction. Something like this is the sandwich-like structure. You can say this bending is very small. And second, we choose results, go to the transformation. We want on our result put in lay up orientation so that the E11, E22 will align the oriented material direction. Okay. Now, because we want to compare these two, so it's better that we can view these two together. We just click viewport and create, and then click it, or then maybe vertical. Yeah, so the side by side. So for left side, we make it only the laminate. Right side, we make it the sandwich-like material. Then we can click this. Okay, sorry, I forgot to mention one thing. Once we finish the mesh, we can create a set, create an element set. For example, that's at the middle of somewhere, set up this. So later we can just compare this set, the string of this set. And in this case, I already create the element size, so you can see where it is. If I highlight it, it shows here. Okay. Then we just replace it, so it only shows the elements that we selected. Then we click results section. Then we can make component 1E. We can compare E11 and apply. Okay, then for the similar for the sandwich structure, we click this one, and then maybe I didn't. We can highlight what we select. So this is the same location as this laminate material assignment because the model is the same. We only change the material property, then replace it. Then go to results, action point. We also want E11, layer 1, E11. Okay, compare these two, you will find for the sandwich structure, the string component is almost one order smaller than the laminate, which means the right structure has less deformation, one order less deformation than this left one under the same load. Then we compare the another, like for example, the layer 3. Okay, go here, we go to layer 3. We compare this two. Actually, it's also about 10 to 8. Like this is 8 times or 10 times smaller than the laminate one. Also, we can compare the laminate 4, the layer 4, and here also this is already layer 4. We just compare layer 3, and this is layer 4. So that is also smaller. Similar, we can compare the E22. For the E22, the layer, for example, layer 2. So it's 1 power negative 4. Sorry. Then here, we also compare E22 layer 2. So you can say it's almost like one order smaller than the laminate material. Except the string parts, we can also compare deformation. So now we recover it, show all the element. Then we would like to view in yeah, X is okay. X is okay. So you will say just double check if the deformation is scale is 1. Okay. So you can see the deformation is very different between these two. For the laminate material, this material, it has a larger deformation than our sandwich material. So that we can make a conclusion that the sandwich structure is better than the laminates for the same load. Okay, thanks for watching.